So oftentimes when people talk about nature, now we're moving into sociality. Oftentimes people focus on primates and talk about nature, red tooth and claw. So you'll often hear people discussing primates and they'll focus on that they fight. That here we have a large chimpanzee, 3 other chimpanzees, and they're all bearing their massive canine teeth that will tear you up. Some people used to have baby chimps, and they were like, oh, it's so cute, that little baby chimp. And they didn't realize that these things are strong. That a chimp will, after a couple of years, tear you up. They have really big teeth, and they're really, really powerful. And people say, ah, yes, nature is red and tooth and claw. All they're trying to do is attack each other. The truth is, however, that primates engage in lots of reconciliatory behaviors. Lots of them. In fact, most of their time is spent engaging in these reconciliatory behaviors. They do things such as share food. Now, very often they share food with their family or if they want sex, but they share it nonetheless. They spend a lot of time grooming each other. I should have a picture of this. There we are. Here are some baboons. Baboons and chimps and gorillas spend a great deal of their day looking for vermin in their fur. They spend a lot of time doing this. And if you think about it, it's actually kind of essential because it helps keep them healthy. And right after there's been a fight, you find that primates will engage in this kind of behavior to restore the balance. So they don't just fight, they also come back together and say, okay, we need to establish harmony again. We call these reconciliatory behaviors, or they do behaviors to de-escalate conflicts. Because conflicts are really, really disruptive. So we really want to focus on the fact that they also have this. Humans have a lot of this kind of behavior. What's reconciliatory behaviors in humans?
Make-up sex.
Make-up sex.
I was just going to say.
I really like how you went there immediately. You didn't even, it's like, you didn't give any other options. You were like, no, we apologize.
Everyone was thinking it, and I felt
everyone was thinking make-up sex. All right, we can take a vote. Who was thinking make-up sex is the first thing?
Let's take a poll.
That's actually like the main method of reconciliatory behavior for bonobos.
Yeah, for bonobos, they are the sexy chimp, right? Yes, they engage in a lot of sex, right? So yes, unfortunately, most of my fights do not end that way with bonobos or humans. But yes, make-up sex would be another one of them. You can think of apology being one. Just mundane way. What? There's lots of these. But they de-escalate the conflict. Or if two people talk to each other and say, hey buddy, you need to calm down a second. Let's go outside. That's a way to de-escalate a conflict. So this is part of being a primate as well, engaging in these reconciliation behaviors. So what I want to do for the rest of today is explore some of these biological bases. I want to explore some ways in which primates seem to engage in behaviors to keep the troops together. And it's going to be the focus for today and Wednesday to show biases that primates, not just humans, but primates show a number of social biases, which we're so used to them that it doesn't strike us as weird, but they really kind of are in terms of all species. So I'm going to explore some biological factors, and I'm going to show how primates evaluate social situations in a way that a cat or a iguana would not do so. I don't really talk much about iguanas. I don't like them. I had a college roommate that had an iguana as a pet, and I was like, it's not a pet. And he kept it in our bathroom, and I hated the thing. That's a true story. All right, brain. The first thing we can focus on here is the brain. Primates show, the primate brain seems to be sculpted to deal with social factors. Now, what do I mean by that statement? Well, if you go across all sorts of animals, you can do a very simple correlation. Remember, we discussed correlations, and I said we're going to come back to them. And what we can do here is we can correlate an animal's body weight, that is how much does it weigh, and its brain weight. And you can, every animal's going to have a body weight, an average body weight, an average brain weight, blah, blah, blah. And what you find here is you can make a regression line. So this is your predicted brain weight from body weight. And what you find here is that primates tend to have a larger brain than you would expect given our bodies. Our brains are a little bit larger than you might predict in the aggregate. And primatologists and physical anthropologists are interested in this because they say, well, I would expect a certain size, but we have more. As the brain is, can you hear the door? Yeah. And as the brain is a very metabolically expensive organ, we wonder why our brains are so large. And so what we can do here is a very simple analysis. We can take a bunch of species, plot their brain weight and body weight. So you get a goldfish. The goldfish is not very bright. It falls under the regression line. Apparently possums aren't either. Ostriches aren't either. I was surprised to find that lions aren't. I wouldn't say that to their face. But you can see, if you go up here, primates have much larger brains than you would expect by chance alone. And the way in which anthropologists and primatologists discuss this, they say, well, we can have the actual brain size compared to the expected brain size. So we have the actual brain size compared to the expected, and we call this the encephalization quotient. Now, that is a fancy, fancy word. And y'all know I love fancy words. You know this word, Byron. You're going to know this one. Cephalo. What does that mean? If I say someone has cephalitis, what does the word cephala mean? No one knows? It just means head. EEG is what? An electroencephalogram. That's the same word. It's the same word here. So if EEG is electroencephalogram, the second E is encephalo. It means head. So an EEG is a graph of writing of electrical stuff from the brain. All right? Well, quotient obviously just is a divisor. That's this fancy word. So I have my actual brain size over my expected brain size. And this gives us an idea of how to conceive of several organisms. So if the encephalization quotient was 0.5, this would be, I expect an animal to have a brain like 2 pounds, but it only has a brain of 1 pound. Why? But if you had one, let's do it like this, where I expected it to have a brain size of 2, but it really had one of 4, I would say its EQ was 2. And saying EQ of 2 means it has a brain twice as large as I would expect. This one has 1/2 as large as I would expect. And looking at this diagram, humans have one that is much greater than 1. Primates in general, and humans in particular, have a large encephalization quotient. How large is it? Well, we're going to see. It's actually really, really, really large. But any questions about this encephalization quotient notion? It's just as a way for us to think about brain size across organisms. And it's just comparing the expected to the actual. Humans score high on this. And what's really intriguing, and here's where we're going to get into the meat of today's lecture, is on the lineage leading to humans. So if you go back in time and you go back 100,000, 200,000, 300,000, 1 million, 2 million years, you eventually find where the primate lineages start splitting off, the common ancestor with humans split from the common ancestor with chimps, and you go off in a certain direction. And what you find here, though, is as you go on the lineage leading to humans, the EQ is getting bigger and bigger and bigger. So if you take a primatology class or physical anthropology, you'll learn about a species named Australopithecus. I happen to have an Australopithecus on my shirt today. I only get a chance to wear it every so often because it's just kind of nerdy. I went and saw one of those famous Australopithecine fossils in Houston. It's very, very excited. I got the t-shirt to prove I was there. Australopithecus named Lucy, hence the I love Lucy joke that, sure it is. So you can all go, that's what he's talking about. Because when they found it, the story goes, they were listening to the Beatles' Lucy in the Sky with Diamonds, or doing LSD, I'm not sure. One or the other. All right, so this is a species named Australopithecus. Now, a bunch of stuff goes on. There's other Australopithecines that I don't care about, the Robustus and so forth, boy's eye. I don't really care about those because I'm like, they didn't lead anywhere that I care about. But then you have a species that is on the line leading to modern humans called Homo habilis. Homo, man, habilis, handyman. That's what his name means. Homo is the handyman. Then you have a species named Homo erectus. Stand upright man. That's what Homo erectus means. You're really making all sorts of jokes there? That's okay. Okay, That's well, you know what? Technically you're a homo too, You're gonna make the joke. It just means that's a different homo than this homo. That homo comes from Greek, this one comes from Latin. And so finally we get up to modern humans, Homo sapiens. We weren't at all humble about naming ourselves wise man. That's what our name means, wise man. I always think if other animals got to do the naming, they might do it a little different. But all right, our name would probably be Homo litter box cleaner or something. Would be my name. So what's interesting? So we do have to know the order of these species, going from Australopithecus, habilis, erectus to sapiens. So you can make a little mnemonic like HES or something, HES. If you were thinking habilis to erectus to sapiens. Because what we can do here is we can actually go out and find the fossils of these species, and we can compute their encephalization quotients. And what we have here is just a chart, and I'm going to tell you the take-home message from this chart. What we can do is we can start with a species like the chimpanzee. All of these things have a Latin name. Remember, it's the Linnaean nomenclature system. We have a species name and a genus name. So we have Homo as our genus, Sapiens as our species name. Well, for chimpanzees, they're called Pantroglodytes. That's just their name. So what you see is their encephalization quotient is about 2.5 times bigger than we would have expected by chance. Lucy, the Australopithecines, theirs is a little bit bigger. And you can keep doing this analysis. Homo habilis, notice this is the number that we are intrigued with. Homo erectus, notice it keeps going up until we get to modern humans who have a brain nearly 8 times larger than we would expect. That's huge. That is huge. Graphically, it looks something like this if you actually want to look at some fossils. So here we have an Australopithecine, Homo erectus, and a modern human. Our brains have increased dramatically in size. Why? One dominant answer to explain this is socialness. And so what we have to do to explain this is we have to get an indice of social complexity. We have to understand what it means to talk about social complexity to understand why we would need a big brain to deal with it.